Okay, so this combines the last two sections into one lesson. Again, like I did with the tangent line problem, I kind of present it right up front because it kind of motivates why we do the limit process. But those limits were different than these limits. Right? These are limits as x, or in this case, n, approaches infinity. Not as it approaches some, as they said in their definition, arbitrary number c, right? So it's a little bit different. So limits at infinity and the limits of sequences and the area problem. So the area problem that they're talking about is how would you find the area when it's not a regular shape? I mean, we've got a lot of formulas for triangles and trapezoids and circles and all that stuff, right? But what if it's an irregular shape? And this is an example of a function, right, whose graph is, you know, if you use that as the top of the shape, and this vertical line, x equals a, and this vertical line, x equals b, as the left and the right, and the x-axis is the bottom, that's an irregular shape. We don't have a way to calculate that shape exactly. In the book, they do say that civil engineers can use calculus, this kind of thing, to estimate the areas of irregular plots of land. I mean, if you go back in, you know, ancient history, a lot of what they did with geometry, which started with the Egyptians, was to come up with formulas to estimate the area of land so that they could do taxes based on how much land you had, right? That's where a lot of the formulas we have for geometry come from. Just a second. I actually prepared for this one, you know. I want to make sure I say the right things. So that's what the area problem is. How are we going to find this? Well, how we find it is, at least the thinking, the thought process that we start with is, how about if we take some regular shapes, like rectangles, and see how many of them we could fit under that shape, right? That would be an estimate. We would know how to find the area of each individual rectangle. I mean, in this problem here, the top of the graph is f of x equals 6 minus x squared. So it's a parabola, the y-intercept is 6, it opens down, and we're trying to find the area only between x is 0 and x equals 2. And you could see in their picture there, they've used 5 rectangles to estimate the shape. Okay, so what would be in order to find the area of a rectangle, you need what? Length times width, right? And the width of the rectangle is going to be, right, from 0 to 2 divided by 5, 2/5, right? Every one of these rectangles is going to have a width of 2/5. Okay, now, how high is the rectangle? Well, you can see, notice the way they've drawn their rectangles here. Right? This first rectangle goes as high as the graph is on the right side of the rectangle. So I would need to know what is the value of the function at this x value. And what is that x value? 2/5, right? If this is 2/5, right? X equals 2/5. So this value of the function right there would be f of 2/5. So just knowing that there, I can come up with the area of this one particular rectangle. And then I can do the same thing for the next 4, right? I'm always going to have the same width of the rectangle, 2/5, and then I just have to find the value of the function at x equals 4/5, and 6/5, and 8/5, and 2. And then I'll have all the areas. Now, will that be an exact estimate or an exact calculation of the area under the curve? What will it be missing? All these little light purple areas right there are actually being missed. Our area would not be equal to the total area because it'd be missing all of that. You know, it depends on the shape. It could be that your rectangle extends outside the shape, right? So that would be another kind of error. But this is just an estimate, right? The area of a rectangle is the length times the width. So if we add up a bunch of rectangles, we'll use that as an estimate. Okay, so this shape here, I'm trying to remember because I'm reusing this, but I think I took that from the sine wave, right? And I'm going to use I'm trying to find the area in between x equals a and x equals b by using two rectangles. And you could see that, you know, we would, and so I'm going to add up. I'm using the summation notation, something we've done before. I mean, that's what's so good about this last lesson, is it ties together a lot of things we did before. Right? I'm going to add up the rectangles. I'm using an index of I. So I equals 1 to 2, length sub I, width sub I, right? So it'll be length times width, add them up. Okay. Now, the width of each one of these is going to be b minus a divided by 2, right? That's the width. Right? And then we're going to find the function value. We're actually finding it at the right side of the box. So this is the x value that we're evaluating the function at, f of, right? It starts at a, and this is saying let's add one width, right? Because the width is b minus a over 2, and it's got an index of I. So when I equals 1, we're adding one width to the right of a, right? And then we're calculating. That'll be the height of the rectangle. And then when I equals 2, we'll be adding 2 times the width, so we'll be right there. And does that look like it'll be a very accurate estimate of the area underneath the curve? I mean, it's missing this piece here, and it's got some extra pieces here, and all the orange stuff there. That's extra. So, I mean, they would certainly work against each other, but it still looks like it wouldn't be very accurate, right? There's a lot more of the orange that's not in the graph than there is the white that is. So it's not going to be perfectly accurate. And, you know, in real calculus, right, you could also, you know, if you wanted to use the left side of the interval, you could, right? You'd get a different estimate if you did that. So now I'm using the function value here and here. Is that going to make it much better? I mean, I'm still missing all that stuff there. Or actually, this is extra. No, I'm missing all of that, and that's extra. And I'm missing that there. Or sometimes, as you're doing this kind of stuff, maybe you could use the midpoint. You know, try to get like halfway through the box. That would be another way to do it. So right in the middle of the box, go to the graph. I mean, there's ways to make your formula then go to exactly to that, if that's what you wanted to do. But we're not doing it. All these formulas are based on us using the right side of the rectangle to estimate the height. Okay. And you'll see, if and when you get to calculus, that sometimes you use trapezoids too. That's another shape. We know the shape of a trapezoid, so use a bunch of trapezoids to do it. Okay, so now what happens to our estimate if we increase the number of rectangles? Right? So now my width is b minus a over 4, and I'm still using this here. I mean, what's changed? Okay, now because the width is b minus a over 4, that's counting widths to the right. Right? So this is the width. Oops. This is the width. This is the height. Oh, actually the length. But it's the height. Okay, so as I increase, I get a little bit better estimate. What if I go to 8 rectangles? Even better, right? Even better, right? But now my width is b minus a over 8. So now I've got an 8 there, there, and there. So this should suggest that, well, what if we just keep increasing the number of rectangles? Won't it maybe the value of this sum of the rectangles get closer and closer to the actual area? And yes, you would, right? That's what we're going to try to do. Let's see what happens if we keep increasing the number of rectangles that we use. And to do that, then we're going to say that the area is, and now my index of the summation is going from 1 to n. From 1 to n. And so the n, remember when it was 2 and 4 and 8, that number showed up there and there. Everything else was the same. And then we're going to see what happens if we take the limit as that n the number of rectangles approaches infinity. And I think I'm missing the right side of that. Right, so it's an approximation. That's why I'm using like the little wiggly equal sign. It's approximation when I'm actually adding up a finite number of rectangles. It is going to be equal to the area if I can take the limit as n approaches infinity of the length times the width and add them up. Okay, so that a limit as n or x approaches infinity, that's a different problem than the limits that we already did. Has different rules, but in the end, they're kind of familiar rules. They're rules that you've used before in this class and Algebra 2, and ultimately, they're pretty easy. So all of this is taken from the 12.5, the area problem, just trying to describe why is it that in 12.4 we're doing this limits as n approaches infinity, right? This is the reason why. What's that? Okay. I'm sure it was good. I'm sure it was good. Okay. I don't think I said that. You might have heard that. Okay, are we good on that? So, back to 12.4 to talk about how do you take limits. And this is going to kind of take this is the way they do it. This is the way they reveal it. And it is a little bit useful, but the limit as x approaches infinity of 1 over x to a power, right? As the x grows, what happens to the value of the function? Since the x to the r is in the denominator, as this gets bigger, the fraction gets smaller. It'll approach 0. Any function which has got x approaching infinity and it's 1 over x, that fraction is going to get infinitely small. It'll approach 0. And if you notice the way they've done that, they're saying x approaches infinity and x approaches negative infinity. So it's either direction. Either direction. So here's a limit as x approaches infinity, 4 minus 3 over x squared. Now remember, we can take the limit of a sum is the sum of the limits. In this case, it's a difference. So the limit of a difference is the difference of the limits. So you could break it up into two terms, right? So let's do that. Right? This would be the limit as x approaches infinity of 4 minus the limit, he's back, as x approaches infinity of 3 over x squared. Okay, we've already done this. Same properties of limits. What is the limit of a constant? It's the constant. So this part is 4. And then based on that last slide, right, when you're taking the limit as x goes to infinity of, theirs was 1, okay, this is 3. You could use another property of limits and just take the 3 out front. But in any case, 3 over x squared as x approaches infinity will approach 0, right? This whole fraction should approach 0. So the limit of this function is 4 minus 0. 4. We're good? Anna? Okay. So this is the first part of example 2. It says find the limit as x approaches infinity for each of the functions. So far we're just going to do the letter a. Okay, so the limit as x approaches infinity of negative 2x plus 3 divided by 3x squared plus 1. So I'm going to show you how they're doing it in the book right now. And then later I'll show you probably the way you'll really do it, which is not like this. But I've heard the calculus teachers talking about this sometimes, about this particular thing, which is, what do you see as the highest power of x in that expression? X squared, right? So divide every top and bottom, every term, by x squared. Right? Oh, that was wrong. Just x squared, x squared. So I've just multiplied by 1 over x squared divided by 1 over x squared. Right? Same, it's 1 in the end. And now if I simplify this, this will look like the limit. Right? In the numerator, it's going to be this x will cancel with one of those, so it's minus 2 over x plus 3 over x squared divided by 3 over, no, just 3, because the x squareds cancel, and then plus 1 over x squared. Okay, now, as the limit as x approaches infinity, every term in there except for the 3, it's a constant divided by some power of x. So what will happen as x approaches infinity? They're all going to go to 0, right? I mean, this will go to 0, this will go to 0, this will go to 0. So this is going to be 0 over 3, which is 0. So you could take every one of those, yeah. Yeah, that's what I'm about to show you. Okay. So this is what you're going to see if you look in the example. Okay. That should be kind of familiar. What he's saying is, wouldn't you just go to this and say, since the higher power of x is in the denominator, that it could, I mean, actually, that wasn't, we weren't doing limits back then. What were we actually finding when we did that? What's that? That's a horizontal asymptote. And that's all limit as x approaches infinity is. It's the end behavior, basically. Right? We saw this before. This is taken from chapter 2 when we did vertical and horizontal asymptotes of rational functions. These were the rules, right? It said, if you have a rational function, a polynomial in the numerator, a polynomial in the denominator, the highest power term is x to the n and x to the m with coefficients of a and b, right? If the what this saying is here is that when the n is less than m, the power in the numerator is less than the denominator, then y equals 0. In our case, we would say the limit equals 0. If the n equals m, they have the same highest power, then it's the ratio of the coefficients, a over b. And if the numerator has a higher power than the denominator, there is none. There is no horizontal asymptote. In this chapter, that's what the way they say it. But it's the same thing. Right? There's the function, polynomial in the numerator, polynomial in the denominator. Right? They've each got their highest power and coefficient. And now we're going to say the limit as x approaches plus or minus infinity of f of x. If the n is less than m, 0. If the n equals to m, the ratio of a over b. Right? If n is greater than m, the limit does not exist. I mean, that's one for one what we just did with the horizontal asymptotes. So these rules, you did them before. I don't know how successful you were with them, but that's all you've got to do with these. Define the limits. There is sometimes that there's a little bit of a combination of the way I did the first example and this, which we'll see in the ones that are coming up. I mean, remember that using these rules means you have a rational function. I mean, it's all numerator divided by all denominator. That's one term. If you have more than one term, you're going to have to split it up, right? So now, if we know these rules, wait for everybody. Good. Now we can go back to these are all three in that example. We already just did the first one. And again, you would have looked at that and said, the highest power is the denominator, so the limit as x approaches infinity of f of x equals 0. Right? Okay, this one, they have the same highest power. So what is the limit? The limit as x approaches infinity is negative 2 over 3. How about this one? Right? The highest power is in the numerator, so no limit. Meaning it's going to veer off. In this case, it's going to be negative, so it'll veer off towards negative infinity. Good. All right, so let's do these three. Limit equals okay, how about this one? What's the limit? 0, right? Highest power, denominator. What's the limit? Okay, highest power, they both have x to the first, so it should be the ratio of the coefficients. 2 over negative 1, negative 2. How about this one? Its highest power is the numerator, does not exist. All right. So these are different rules than we learned for limits as x approaches c, right? Some arbitrary number, but they're actually pretty easy. Okay, the limit of a sequence, right? I mean, there's no difference whether we did this with x's as a variable or whether x is the variable, the independent variable, and the function f of x, or whether you use n as the index of a sequence, a sub n, right? A sub n is like f of x. What's the difference between those? And not just notation. Remember, n is a counting number, right? 1, 2, 3, 4. X is a real number. It can be any decimal fraction, anything. But this is just going to be the counting numbers. But as long as we have an expression that represents the a sub n, and it's like a rational expression that we just dealt with, we're going to use the same rules that we just did. Right? Just look for where's the highest power. I mean, if you remember the slides we did from 12.5, the area problem, that is the kind of limit we had to find, right? We didn't have a x approaches infinity. We had an n approaches infinity. So we go back and we talk about the limits as x approaches infinity because it relates to something we did before, horizontal asymptotes. And now we just take a step sideways and say, okay, well, we can do the same thing as n approaches infinity. Okay, so let's say the limit as n approaches infinity of a sub n equals, okay, in the first one, right, which rule are you going to use? They have the same highest power, so what is the limit? 2 over 1. 2. How about the second one? Right? The highest power is in the denominator, so the limit as n approaches infinity of a sub n equals 0. And how about the last one? Right? Same, so it'll be the ratio of the coefficients. The limit n approaches infinity of a sub n equals 2 over 4, which is 1/2. Easy stuff, right? Good. Okay, let me know. Okay, just do a few more. I added more in here because they're so easy, right? We can just go through. The limit as n approaches infinity of a sub n equals, how about the first one? 1/2. How about the second one? Right, the same highest power, so it's 1/3. How about the last one? Highest power in denominator means 0. Now, most of the time when you use those, actually, to do completely what you do in section 12.5, they're a little more complicated than that. But in the end, they work the same. And if you could just see your way through a more complicated expression, which we will now, it's actually not that tough. Find the limit of this sequence. Now, remember, what's the only thing you're looking to decide what the limit is? You're looking to see what's the highest power in the numerator, what's the highest power in the denominator, and then apply the appropriate rule, right? So in this problem here, we want to take the limit as n approaches infinity of a sub n, that's sub n, a sub n, right? All we really need to know is what's the highest power and what are the coefficients on the highest power terms. I mean, in the numerator, it's going to be 2n times n times n inside the brackets here, right? That'll be 2n to the third times 8, 16n to the third, right? I mean, I can FOIL this and multiply by n and then multiply by 8, but definitely the first term is going to be 16n to the third. And then there will be terms that follow, but they won't determine anything about the limit, right? So all I'm doing so far is I said 2n times n times n times 8. That will be the highest power term. Okay, and what will be the denominator? 6n to the third, right? So, and that is the whole denominator. There's nothing that follows. So just based on that, which rule do I apply to find the limit? It's the ratio of the coefficients because they have the same highest power. So what is it? 16 over 6, which is 8/3. Right? You could FOIL, you could come up with all the terms that are in there. I mean, it's not going to be that many. What that would give us 3 terms, and then you multiply by 8, and it's still 3 terms. But in the end, you don't really care about what follows the leading term. It doesn't have anything to do with the limit. So just get that first one of the numerator and denominator. If they have the same highest power, and they almost always do when you get to this kind of problem, then just take the ratio of the coefficients, 8/3. All right, so let's try the same thing here. I mean, the first one is going to work exactly like the one we just did. right? What is going to be the highest power term in the numerator? 2n times n times n times 5. What is all of that? It's 10n to the third, right? And there are some more terms that follow. They're all lower degree, so they're not going to affect our answer. And what is in the denominator? Right? 7n to the third. And since they have the same highest power, the limit as n approaches infinity of a sub n equals 10/7. Now the next one's a little more complicated, right? Because it's not a rational expression. There's two terms inside of there. So you probably want to simplify it a little bit before you start. I mean, I can go like this, right? Let's distribute the 2 over n. Right? That's going to give me a sub n equals the 2 over n times n is going to be 2. And now the 2 over n times 2 over n is going to give me minus 4 over n squared times bracket, parenthesis, okay, now when I take the limits, right, the limit as n approaches infinity, okay, now I'm going to use the properties. Let's go term by term. See the question? Okay, right. What is going to be the limit of 2? 2, right? And the limit so this one we've got, that's 2. And then the second one, what is going to be the highest power term in the numerator? N times 4, right, that's 4n squared. And in the denominator, it's 4n squared. So they have the same highest power. I should have said plus dot, dot, dot. They have the same highest power, so it's a ratio of the coefficients, which is 1, right? So that's 2 minus 1, which is 1. Yeah.
So with that, like, minus, like, and you have the higher power on top, so that means it's
Yeah, if one term has a limit and the other does not, then what do you think? Altogether, they don't have a limit. It's a good question. I don't remember if it comes up in the homework. But it has in past years, but it's a new book. I don't remember exactly. So that's the kind of limit taking you end up having to do when you do the problems that are in section 12.5, which we're not doing any actually, okay? But we do need to know how to do that part. They're not all going to be as easy as the first ones we did. Most of them will be. Okay, so I'm just going to show. You don't have to copy any of this down, but just to show how that happens. Like, let's say, this is coming from section 12.5, that we wanted to find the area under the curve, f of x equals x squared, between 0 and 1. So that, in our slides before, that would have been the A and the B. Okay. Then we would be trying to find, right, estimating by adding up the areas of rectangles, right? That's the summation is the adding up part. I equals 1 to n, right? This is the width of the rectangle, right? This is the length times width. It's also the height, you know, of it. But so this is what we had before. We're taking the limit we're finding the sum 1 to n of the length times the width of all the rectangles we're going to add up in between those two. Okay. Now, the b minus a, we know what they are, right? So we don't need to keep b minus a. B minus a is 1. That's how they can go from this to this. B minus A is 1 over n. Right? B minus A, 1I over n, and that's a 0. So then what they didn't show, since it's x squared, if you take I over n and you plug it into x squared, you get the I squared over n squared. Okay, now simplify that, right? That's I squared over n to the third. And now notice what they did from this step to this step. The n is actually a constant. It's not changing, right? It's not being changed by the summation. So we can actually pull the n to the third out in front. So 1 over n to the third times the summation from 1 to n of I squared. Now, you probably don't remember us doing this before, but we actually worked with formulas like that way back in chapter 9 when we were doing math induction. Remember, math induction was a way for us to prove formulas like this for all values of n. We were given an expression, or we were given a summation, and we would have to plug in and show it worked for n equals 1, and then show that if you assumed it worked for n, that it must work for n plus 1. In that way, if it works for 1, it has to work for 2, and if it works for 2, it has to work for 3, and so on and so on and so on. And we proved a lot of these formulas back then, or at least we saw them. But we probably did this one back then. The sum of I squared is this formula right here. So now we can go back to the previous slide and replace this part of it with that. So that's what we do. So we're going to replace this piece right there with the formula that we've already encountered once before. And now that's looking a lot like the limits that we were just taking. And that is the last thing we've got to do. They actually simplified this. They didn't just take the highest power term. Although the highest power term you can see is 2n times n times n, 2n to the third. Right? This stuff isn't going to matter anyways, but they gave us the whole thing. And the denominator is 6n to the third. And now we're define the actual area, not an approximation, so we don't need the wiggly equal sign anymore. It's actually an equal sign. The actual area underneath that curve will be the limit as n approaches infinity, as the number of rectangles approaches infinity, of this expression for a sub n. And again, since the highest powers are equal, then it'll just be the ratio of the coefficients, 2 over 6, 1/3. So that's the area under the curve between 0 and 1 of x squared. Almost done. One more slide. So this process, the limit as n approaches infinity, right, is called integration. In calculus, that's called integration. Integrals give us a means to calculate the irregular areas, like the area under a normal curve, right? Whenever you do calculations with normal, you need to know like what percent of the area is underneath the curve. Well, you know, that's where those kinds of things come from. The area under irregular shapes, that does it. But it's also exactly the opposite process of differentiation, finding the derivative. I mean, just think of it. If you have an x and a y, right? If you have an x and a y, y over x is the slope, right? But x times y is the area of a rectangle, right? The x times the y is the area of a rectangle. Those are inverse processes, right? If I say f of x equals x squared, and then like I showed you before, that means f prime of x equals 2x, right? I bring down the 2, reduce the exponent by 1, okay? Then we would say the integral of 2x equals x squared. They're inverse processes. There's a little more to it than what I'm showing you right there, but that is, in the end, taking the integral and finding a derivative are inverse processes. Okay. Okay. You okay? So that's it. Now, these are all odd numbers, and they're all as easy as the ones that we did, like 12 of them right here. You know, just compare the numerator and denominator. These are with sequences, the same thing. It says find the first 5 terms, but don't worry about finding the first 5 terms. Just find the limits, okay? And then these two get added on. I think they're more like more complicated, just comparing the highest power terms. Yeah. None. But there will be limits as n approaches infinity or x approaches infinity. Right? There's no homework that's coming from that last section. Right? It's only coming from 12.4.